Hello and welcome to this new tutorial. Now it is time to implement the V part of the VAE, meaning we're going to implement the stochastic way of getting the final latent vector Z. Because indeed, right now we are at this specific step where we've just flattened the result of these four convolutions into a one-dimensional vector of 2 times 2 times 256 elements. And that would be the final latent vector of a classic autoencoder. But here we're building a variational autoencoder, and therefore instead of returning this latent vector Z in a deterministic way as a result of these four convolutions, well, as you can see, we're going to sample it from a factored Gaussian distribution of mean, mu, and variance sigma. So the way we're going to do this is we're going to make two separate fully connected layers, mu and sigma, and we're going to build them with the dense function by TensorFlow. That's why you see dense here, and dense is always the name of the classes and functions to build fully connected layers. And then using the random normal distribution by TensorFlow, we're going to generate or sample some numbers from a normal distribution, meaning a Gaussian distribution of mean 0 and variance 1, and we're going to add all this to obtain the final latent vector, which is the result of some stochastic operations. Therefore, is given in a stochastic way as opposed to a deterministic way. So let's do this. Let's build these two fully connected layers, and then let's sample our final latent vector Z from the factored Gaussian distribution. So back on Python, here we go. Let's start with the first fully connected layer, which is mu. So I'm going to introduce a new variable here, self.mu, which is going to be, well, a fully connected layer, which we can create thanks to TensorFlow the following way. We're calling first TensorFlow, and from TensorFlow we're getting first the layers module, and from the layers module we're going to get the dense function. And this function is going to take three arguments that we have to specify here. The first one is going to be the input vector of this fully connected layer, as in an artificial neural network, which you saw in step 1, artificial neural networks. So what do you think is going to be this input vector here of this fully connected layer? Well, of course, that's going to be the flattened vector resulting from the four convolutions, and therefore it is going to be h. And then, as a second argument, we need to specify how many neurons we want to have in this fully connected layer, or how many units, as it is the name of the argument here. And well, to figure out what this number is going to be, we just need to look again at our architecture made by the authors. And since actually we're going to sum these two dense layers with this normal distribution here multiplied to sigma, well, actually the size of this first fully connected layer is going to be exactly that size here, because that size is the size of Z here, and Z is the sum of these two layers. And therefore, what we want is 1024 units in this first fully connected layer. However, this number is actually the Z size argument here. That is one of the arguments of the init method, meaning of the future instances of the conv-VAE class when we create them. And therefore, we don't have to specify 1024 right now. We will specify that later when we enter the argument value here. And therefore, we can just input self.zSize. Here we go. Right, perfect. And then, as usual, we can, add a name to that specific layer. So I'm just going to get this, and we're going to replace here enc_conv1 by, well, we can still say that we're in the encoder, and we're going to replace conv1 by fully connected, because we're building the first fully connected layer mu in the variational part of the VAE. So fc, and then we can just say mu. All right, so we got the first one, meaning we got this one. And now let's build this one, sigma. So it's going to be the same technique. So I'm going to copy this, then paste it below. We're going to replace mu by not sigma directly, but by log variance, log var, because actually log var is going to be what's inside the exponential in the Gaussian distribution, right? And log var is going to be exactly the fully connected layer inside the exponential, which is going to take again the latent vector h as input, which was returned here as the result of the 4 convolutions. Then same z size again for the same reason, because we are summing these two layers to get the final latent vector z with the 1024 elements, which corresponds exactly to z size. And now for the name, we're going to replace that ong_fc mu by, of course, ong_fc log var. Alright, so that gives us what's going to be inside the exponential of this second part of the sum here, mu plus sigma multiplied by the normal distribution. But since we actually want a Gaussian distribution of mean, mu, and variance sigma, well, of course, now we gotta take the exponential. And so, to get it, well, now is the time to get sigma, and therefore I'm introducing this new sigma variable as a variable of our object, so self.sigma, and self.sigma is exactly going to be the exponential of log var, but, divided by 2, because in the formula of the Gaussian distribution, in the denominator you actually have 2. So let's take that exponential. We're going to get it by TensorFlow, so I'm calling TensorFlow TF, from which I'm going to take the exponential function, inside which I'm going to enter, of course, self.log var divided by 2.0, because this is a float operation. And perfect, now we get the second fully connected layer, sigma, and so now we can just sum these two, but sigma is of course going to be multiplied by the random normal distribution. And the random normal distribution is actually a function again by TensorFlow, which is the random underscore normal function, and that's exactly what we're going to use to compute that final sum. So let's do this. Let's get that final sum, but first, if you want, we can, get separately that n01, the normal distribution, meaning the Gaussian distribution of mean 0 and variance 1, so that you can clearly see how to get it. And so we're going to introduce that as epsilon, a new variable of our object. And as we've just said, we can get it by using from TensorFlow the random normal function of a list of 2 elements in square brackets. The first one is going to be the batch size. So here we go. That's where we specify the batch size and not right here. We're going to specify this in epsilon here. And the batch size is actually a variable of our object, self.batchSize, which we initialized in the init method. So that's the first element here. And the second one is going to be the size of the latent vector z, which is 1024, and which is given by also a variable of our object, self.zSize. So let's paste that right here. And so now the fact that we create the random normal distribution this way will allow us to get not only a single sampled latent vector z as the result of this sum of these 2 fully connected layers mu and sigma, but the fact that we created this way will allow us to give us a batch of latent vector z's, all resulting from the sum of these 2 fully connected layers, mu and sigma. Alright, so now we're finally ready to get actually now the batch of latent vector z's. And so this is going to be the simple part, because now we have all the elements of this operation right here. So we're just going to sum the first fully connected layer that we created, mu, and this product of the second fully connected layer, sigma, which we created as well, and this normal distribution. So let's do this. We can now get the final latent vector z, and it is going to be, as we've just said, the sum of self.mu plus self.sigma multiplied by the normal distribution self.epsilon. Here we go. Perfect. That implements the V part of the VAE, which you have to understand will allow us to get in a stochastic way, as opposed to a deterministic way, the latent vector z's, which result therefore stochastically from our previous 4 convolutions. Alright, so we have now one more part to go. It is of course the decoder part of the VAE, and we'll do that in the next tutorial. You can actually practice to do it yourself. I'm just going to tell you the function that you have to use by TensorFlow. It's conv2d underscore transpose. So try to do it yourself by just following the architecture here. It's going to be exactly the same as what we've just done for the encoder, except that this time you have to use the conv2d underscore transpose function. So you have all you need to do it yourself with all the information here. So try to do it for practice, and I'll give you the solution in the next tutorial. Until then, enjoy AI.